I will begin with a word of prayer. All right. Heavenly Father, we thank you for this day. I can thank you for these students. Just ask you to bless our work today, Lord. In your name I pray. Amen. All right. So let me remind you what we worked out last time in terms of integrals of a reminder. What was it? What did we figure out? The integral of dx over x to the p. How'd that work out? It was infinity. If p is, what was it? Less than or equal to 1. And it was 1 over p minus 1, was it? If p is greater than 1. All right. So, for example, the integral of dx over x to the fourth we worked out is 1/3. Right. So this is useful for comparison with other integrals. All right, so last time I did integral of x to the fourth plus, integral of 1 over x to the fourth plus 1, and we argued it converged by comparison with the p equals 4 integral, right? Let's look at something a little bit different than that. Example 2. What if we look at like the integral from, let's see here, dx over, let's say 0 to infinity. Let's make it, okay, fine, yeah, 0 to infinity of x minus e to the x. Oh, that's a little bit too much. Let's see here. It's not quite what I want. You fix that, because that's blowing up at, oh, no, it's not. At 0, that's okay, right? I was worried there's division by 0 at 0. That's not a problem, actually. So first of all, is this integral, I mean, obviously it's improper in the sense of the upper bound, right? But are there other places where this blows up in the interior of the integration region, like x minus e to the x? Is this ever 0? How could you analyze that? Is x minus e to the x ever 0? Here's how I'd think about it. I mean, you can look at different arguments, but the way I'd look at it is this is y equals e to the x. Good grief. This is y equals x. What does y equals e to the x look like? Right. I saw some. So e to the x starts out at 1, right? And then it grows exponentially, in fact. Right? I mean, for what it's worth, this goes, that's not very good, but you can see that there's no place where x minus e to the x is 0, because that would be where these two graphs met, right? E to the x starts out in front of y equals x, and it stays in front, because it always grows faster. Another way you could prove this directly would just be to look at g of x equal to x minus e to the x, right? And if you look at, well, I'm going to stick with, I have one argument. Why do I don't need 3 arguments for this. What am I doing? 1 argument's good enough. All right. So, no worries. No worries. At least the only worry we have is the infinity, right? Like, that's it. All right. So how can you handle something like this? Well, I want to use comparison, right? My intuition is that this diverges. I could be wrong. Let's see here. If I was smart, I'd go back to my notes, but I wanted to illustrate some sort of freewheeling examples here for a couple minutes. So we could break this into the integral from 0 to 1 of dx over x minus e to the x. All right, I don't know what that works out to, but it's just a number. Why do I know that? So if we look at f of x equal 1 over x minus e to the x is continuous, right? On 0 to 1. So that's continuous on 0 to 1, which means that the definite integral from 0 to 1 of that function is just some number, right? I mean, I don't know what it is, but it's some number. I could further bound that number if I found bounds for the integrand, but let's just leave it at that. It's a number, right? So it's not going to convert. It's not going to affect either the convergence or the divergence, right? Whatever happens with this example, it's all about what happens at infinity, right? The so-called tail of the integral. All right. Okay, so what would you, comparison, what do you think? Let's see here. This expression, if my intuition is that it leads to a divergent integral, right? I want to find something smaller than this, which also diverges. Right? If a smaller function gives a divergent integral, it follows that the original function must also diverge. Yeah.
Why was that your intuition? Like that it's divergent?
Because it's kind of like a p equals 1. I could be wrong. We'll find out. So is this greater than or equal to 1 over x? What do you think? Is that a legitimate inequality that I've just written? Why is that true? What have I done going from here to here? Right. Oh, I know what's wrong with my example. Why is this example bogus? Well, anyway, so this is funny. So I agree with what you said. It would seem, I mean, I don't think you're wrong. This inequality is true. Because, well, nah. Goodness gracious. The thing is, the thing that's going to get us into trouble is x minus e to the x positive? E to the x is bigger than x, right? Curses. I mean, I need, the comparison theorem is for positive functions, right? So this example is not working out for me. I'm sorry, guys. All right, let's see if I can fix it. All right, I will make it much simpler. I should have started with something simpler. I'm an idiot. Let's see here. So sorry. All right. How about this? 2. And we better start this integral at 3. All right? Okay, so then I would point out that this should be greater than or equal to the integral from 3 to infinity of dx over x, since 0 is less than 1 over x is less than 1 over x minus 2 for x greater than or equal to 3, right? Would you guys agree with that? Why would that inequality be reasonable? Why would 1 over x minus 2 be larger than 1 over x? Yeah, I'm dividing, exactly, I'm dividing by a smaller number, which makes the fraction larger, right? Provided the thing we're dividing by doesn't get so small it gets negative, which was the problem with my previous inequality, right? Because But this we do have, right? So I really shouldn't, I should say, therefore, the integral from 3 to infinity of dx over x minus 2 diverges by comparison with the integral from 3 to infinity of dx over x. Now, you're like, wait a minute, you didn't write it today because apparently you can't be trusted. 1 to infinity is what we proved last time, right? The thing is, it doesn't matter, right? We could also say this, right? By the way, the integral from, say, a to infinity of dx over x to the p is equal to, well, infinity if p is less than or equal to 1, and it's what? It's 1 over p minus 1. Well, I don't know what it is. I have to, it's just some number if p is greater than 1. Now what exactly that number is, I'd have to go back to last class and look at it. I mean, I could do that. It wouldn't take but a second here. What's the number that goes there? What was the integral of, in this case, it was just what? So that's x to the minus p, so x to the 1 minus p over 1 minus p evaluated from a to t. So what is that? Sorry, poor planning on my part. I should have done this yesterday. Oh, it's something. The upper bound. What happens to the upper term here? That goes to 0, right? So this piece goes to 0, given the condition that p is larger than 1. And the other piece is just a constant, which I can more specifically say here is a to the 1 minus p over p minus 1, right? So there it is. Oftentimes I'm interested when the lower bound is 1, so that formula simplifies a little bit. But if it wasn't 1, we just end up with a to the 1 minus p power over p minus 1. So my point here, though, for my example 2, is that, anyway, it doesn't even matter about this nuance that I was just going back through here in the thought bubble. Wait a minute. No, this is in the cloud. So it's in the cloud. Because we just need a divergent case for example 2. Let me do another example. Suppose I was integrating from, I don't know, 10 to infinity of dx over, let's say, x to the x to the 6th plus x to the 5th. Yeah, sure. So my intuition here is that this converges. Because for very large x, what this behaves like is what? I mean, if we think about x becoming very, very large, this is essentially like the integral of dx over x to the 6th. So I know that that is a convergent integral. Essentially, I can ignore the x to the 5th, right? So I'm going to try a comparison. I'm going to say 0 is less than 1 over x to the 6th, right? And that's less than 1 over x to the 6th plus x to the 5th. Right? Certainly that's true for x greater than or equal to 10. I think I could have gotten away with x being smaller here, but I just didn't want to beg the question. I mean, how do I know that this is, in order for my analysis to make sense, I need to be sure that there's no like other hidden divergence between 10 and infinity for the integrand. How can I be sure of that here? X to the 6th plus x to the 5th is equal to x to the 5th times x plus 1, right? So we have zeros at x equals to 0 and x equals to minus 1. So no division by 0 for 10 less than or equal to x less than infinity. Yeah? I mean, technically, we should check on that, right? So do you guys, is this inequality reasonable? It is not reasonable. Why not? Yeah. So let's try this again. I think we could do this, right? And you can tell me why that's true. So you guys are all whispering, he doesn't know what he's doing. He doesn't know what he's doing. It was for your learning, right? All right, this is. And why would that be true? Yeah. The denominator is. Right, this is larger. What she said, yes. Larger. Was episode of The Office. Larger denominator means smaller fraction, right? Because these are all positive. Yeah. Okay. Very good. Thus, the integral from 10 to infinity of dx over x to the 6th plus x to the 5th is less than the integral from 10 to infinity of dx over x to the 6th, which we just learned could be straight calculated as, what was it? 10 to the what? A here is 10. 10 to the, what was p here was 6, so 10 to the minus 5, yeah? Because 1 minus p is minus 5. And p minus 1 here is 5. So there you go. And that integral is pretty puny, isn't it? It's a tiny integral. So anyway, Do you have to compare to the p the p integral? Of course not. Like this is just a benchmark, an easy thing to compare against, right? There are other improper integrals that you can do pretty easily, right? Let's see here, another example. So this one will not be based on the P1. I'll base this on something else. So like 1 over integral from, say, 1 to infinity of dx over x squared plus 1 plus x cubed. So what I'm noticing here is that 1 over, let's say, x squared plus 1 plus x cubed, that would be less than 1 over x squared plus 1, right? And it's positive. But the thing is, this we can easily integrate, right? We can easily integrate that, right? So the integral from 1 to infinity of dx over x squared plus 1, what's that equal to? Yeah, inverse tangent, limit as t goes to infinity of inverse tangent of t minus inverse tangent of 1, otherwise known as pi over 2 minus pi over 4. So we got pi over 4. Thus, by comparison, by the comparison theorem, we have that the integral from 1 to infinity of dx over x squared plus 1 plus x cubed is less than or equal to pi over 4. Which shows that it converges, all right? So it converges to some value less than pi over 4 and greater than 0. Let's look at my notes for a second. I got some better examples in the notes, I think. Uh-oh. Hurry, hurry. Sorry. Poor plant. Here, I know you guys are still copying. We good? I hope so. I'm playing with fire here. There's no telling how many times I can do that before we enter some sort of error state. Come on. All right. Come on. Come on. You can do it. You can do it. You can do it. So first example is actually a picture of the comparison test for 1 over x minus 0.5, right? So so what I have a picture here of is under the green is 1 over x minus 0.5, and under the red is just the p equals 1 integral. So if the red area diverges, surely the green area diverges, right? That's all the comparison test is theoring. The comparison test is saying if you break it back down. Yep.
What do you mean when you're saying a function is converging or diverging?
I mean the integral. I wouldn't say the function is, I would say the integral of the function converges means that the area bounded under the graph in question, the signed area, converges. In the limiting process, whatever limiting process we're talking about, right? Every one of these improper integrals goes back to a limiting process, and saying that that integral converges or diverges is to say that the corresponding limit converges or diverges in the sense of convergent or divergent integrals as was introduced in Calculus 1. That's my fine print. So now, here's another one that was kind of the trouble with my first example. You know, is e to the x less than 1 over x squared? Yes. Excuse me, minus e to the x. Is it less than 1 over x squared? Yeah, it sure is. Is the p equals 2 integral convergent? Sure is. Is the integral from 1 to infinity of e to the minus e to the x convergent? It is not, right? Because I've failed to meet the other condition of the comparison test here, which is that we're comparing a positive function. In fact, we need positive and continuous. The reason that we need continuous, I was guarding against that by looking for zeros, the division by 0 in the integrand. That would lead to a discontinuity in the function. So if that's there, shush, then we have to approach that. So, you know, we have to watch out for that. We actually have to compare to a positive function, okay? That's just... Now, I mentioned this today. Sometimes we don't have to compare integral from 1 to infinity. We can likewise compare integral from a to infinity. And by the way, if you think about it, it doesn't really matter what... If we know that the integral from, say, 1 to infinity of a function converges, right? It's going to be the case that the integral from infinity, excuse me, from like a million to infinity also converges, right? Or 100 to infinity also converges. It doesn't matter where you start the integral. Convergence is really a statement about that limiting behavior as you're going to infinity. So this is what I refer to as the Tail Theorem. If an improper integral to infinity converges for some given starting point, the tail will converge no matter where you chop it, right? So, so here's, you know, some of the mechanics of that. If I integrate from 1 to infinity of 1 over x cubed, you know, if I look from the integral from 1 to 10, what is that? Well, I don't know, it's just a number. And so that's just a number. If this is a half and that's a number, well, this still converges. That's shouldn't be surprising. All right. Here's one that's a little bit fussier. Integral from a to infinity of dx over x to the fourth plus 8x squared plus 3. This example has been written in a very lazy way. Let me translate this example for you. I'm tired. I don't want to figure out where the zeros of this polynomial are, because that's all I'd have to do to make a proper start. But, I mean, this is nice because it frees you of the tedium of figuring out where the zeros of x to the fourth plus 8x squared plus 3 are. Wherever those zeros are, I have to avoid because those are discontinuities in the integrand. And I can only, I'd have to approach those discontinuities in the limiting process we talked about the last 2 days. I want to get past those and just look at the integral of this function where it's positive and it doesn't have division by 0. So let's make a big enough that we're past any of the real zeros. How can I be sure I can do that? How many real zeros are there at most for a quartic polynomial? The denominator. 4, right. If we have an nth order polynomial with real coefficients, we have at most 4 real zeros. We could have none. We could have 2. Anyway, so suppose that, actually, in this case, since we're adding even powers together, a equals 0 would suffice, because obviously if you're adding positive x's together, there's no way you can cancel out the 3, right? But anyway, I can clearly focus my attention from 0 to infinity. I have then that this is less than that. Oh, oh, no, no, no. Oh, man, come on. This will not do. Why is this bogus? Where does the p equals 4 integral start? I can't start at 0, right? How can I fix this example? Let's fix it. It's not hard to fix it. So we're trying to analyze the integral from 0 to infinity of dx over x to the 4th plus 8x squared plus 3, right? And so we just need to use that tail idea I was just talking about, right? That's a typo. All of a sudden I have minuses at the end of this. Yay, yay, yay. I'm sorry, guys. So this we could rewrite as the integral from 0 to 1 of dx over x to the 4th plus 8x squared plus 3 plus the integral from 1 to infinity of dx over x to the 4th plus 8x squared plus 3. Right? Now this right here, this is just a number, right? This is finite because we're integrating a function which is not 0 in the denominator from 0 to 1. This is a continuous function integrated over a closed interval, finite interval. That is just a real number. The other thing here, we can argue that that converges by comparison to what? P equals 4, right? Because 1 over x to the 4th plus 8x squared rather, plus 3 is less than 1 over x to the 4th. And that's also positive. Right? And the integral, we know the integral from 1 to infinity of dx over x to the 4th is equal to what? It's equal to a third, right? We've talked about this. So my example can be repaired, right? And it should be repaired. What's in the notes at the moment is not reasonable. Okay? You know, if you find things in the notes that don't make sense to you, you can email me, and I will try to address those concerns. They are a work in progress, obviously. Well, anyway. Let's see here. I think the next example, I have swapped out the pluses for minuses, right? Well, let me look at this, and I'll get back to you next class. Let me make sure that it's reasonable before I spend class time on this one. I didn't have a chance to look at these before class because I had somebody in office hours. This one here, I think, is better. So suppose we're looking at the integral from 1 to infinity of e to the x dx over sine x plus e to the 2x, right? My intuition here is that this is going to converge. The reason that I think this is going to converge is because I know that the integral, well, to me that looks almost like, it's sort of like an integral of e to the minus x from 1 to infinity. And I happen to know that that converges to 1. Or something, anyway, it converges. That integral is a convergent integral. So the sign is kind of just noise. We want to get rid of it by comparison. So, of course, sine is bounded between -1 and 1, right? And also e to the 2x is greater than e squared for x greater than 1. So it follows then that sine of x plus e to the 2x is less than 1 plus e to the 2x. In other words, what I'm saying is that the denominator can be replaced with this larger quantity, right? And so that would mean that this e to the e over 1 plus so I'm showing that the integral of a smaller thing converges. Does that help? Doesn't help. Ay, ay, ay. Well, apparently I need to rewrite this section of the notes. My apologies, guys. I'm going to just stop here because you got to know when to... This example is wrong. Because, why? What is the problem here? So let me just tell you why it's wrong. I've established this inequality, which I think is legitimate. Okay, great. So this function, which is the given one that we're trying to integrate, is larger than this. Wonderful. And then I show that this smaller integral converges. Who cares? Right? If you show a smaller integral converges, it doesn't prove that the larger function has an integral which converges. It doesn't tell you anything. Except that I got my inequalities reversed in my logic, right? So, anyway, this is a stumbling block for me personally, as you can tell. I am much more attuned to equality than inequality. To me, equality is easy. Inequality is difficult. Yeah.
So can you only use the comparison theorem for when the bounds are 1 to infinity? Or?
Oh no, we could use. There's a comparison from like -infinity to 3. Or even like a finite but improper integral. This is a general result. It's essentially just built over the squeeze theorem for limits. So I should have compared to some. I need to make it smaller, right? So I don't know. I'll have to fix this. I'm sorry, guys. My apologies. Oh, hey, to make it up to you, I'll give you guys a bonus quiz. Everybody get out a sheet of paper. Well, it looks like we'll be on comparison. I was going to move on, but obviously I need to repair the notes and give a mulligan lecture to the last 30 minutes here. I'm so sorry. My bad. But somebody here should have emailed me that this was crazy if you were studying the notes. So bonus quiz. Numero uno, the integral of dx over 1 plus x squared all right. Number 2, the integral of sine to the 4th power of theta d theta. And number 3, the integral of dx over x squared plus 3x plus 2. All right. I will be back in about 5 minutes. All right, guys?